Here we go. Hello, everybody. It's great to see so many people here. Actually, it's exciting. So let me start by introducing myself. I'm Christiane Rütten, and well, to my background, I mean, I started computer quite early, and I was administrator at Institute for Development and Peace, and that's where I learned the Linux basics. And well, lately I switched over to HISA security, maybe you know about it, and that's what I do for a living right now. I'm writing. And well, okay, let me first tell you about this lecture here, because this whole speak has been done for the Informatica Feminale. It's it's a place where a lot of women meet to take some IT courses and to chat. And this course essentially was held this year, and it took about 2 days. It was more kind of like a workshop, and everybody could ask me the questions, which was, in the case something wasn't too clear. And of course, all this isn't possible today. So we will have to see what's going on the slides, and I hope there won't be too many questions, because I had 6 hours for this talk, and well, actually now we have 1. So it's going to be a bit tense. So I hope I won't be expecting too much of you. It will be quite quick, I think, and you will have to pay a lot of attention, I think. And what I expect of you is, well, a good knowledge in a programming language. And you should really know what's going on there. I mean, you should know what is a variable, and maybe you should have heard about the stack and how that thing works and the abstract data types. And you should have profound knowledge maybe in a language like C or Java. And well, maybe you've even seen some assembler or something like that. And that will very much help you. I mean, I won't start by telling about variables and so on, and I will just think you are going to know it, and you should have an idea about how the computer inside works and the bus system and so on. And I'm going to make a very simple model of all this, because you don't have to go too deep into the matter to understand what's going on there. So, well, what all this is here is about is buffer overflow exploitation. And I'm going to present it in a nutshell, and that will be a quite simple view on that, so that we can go through it within 1 hour. We'll start with an introduction to machine language, and I will show you some assembler output, and I will show you some, well, instructions, and we'll see about that. I will show you a simple memory model, which is very much the model that is used by Linux. And this is going to be the platform we are looking at. It's Intel 386 on a Linux platform, because this platform is a very simple platform to understand, and the principles are all the same. It would be a hell of a lot more different and more difficult on a Windows platform, so we're going to do Intel on Linux. Well, then we will see how functions in C are called, because that's where the problem arises. It's actually the buffer overflow problems is a problem of the language you're using, and actually it's a compiler. And so, because most of modern programs and modern operating systems are written in C, this is a problem that you will find quite everywhere. But we are going to concentrate on the GNU C compiler collection, and because it's available everywhere, and I think most of you will be able to go through this at home or something like that. Okay, then we will see what is a buffer overflow, how does it happen, and where actually is that buffer, and what is it we're talking about here. And then we will see how all this can be exploited to let programs do what we want them to do and what they were not designed to do. And therefore, we just need to know what is the shell code. because how can we go on and write a shell code? And I will show you about that. You will see a lot of debugger outputs, and I think it will help you understand what's going on there. And if you've got enough time for that, there will be some countermeasures and what you can do against it. And well, so let's start with an introduction to machine language. And I will tell you about the central processing unit. I mean, most of you will probably have heard it through IT courses anywhere. It's just a very basic and simplified model I'm going to tell. And we will see that the important part will be the registers to understand what's going on into the machine language. And we will go through some example instructions, and there will be a quick note on the endianness, or, well, it's otherwise called byte order. So that's a pretty simple CPU model. And you can see there's a CPU that's attached to a bus, and the bus itself is attached to the main memory, and the CPU is going to fetch instructions over the bus. And there's one thing to say about that, because instructions or data, I mean, you cannot really tell. And it's a question of interpretation. And that's going to be a key point to understanding what buffer overflowing is about, because things that should be data are going to be interpreted as instructions. And that's how all the thing is going to work. What a CPU does is nothing more than some flow control. I mean, like jumps and branches to other points. And it does, of course, arithmetic operations on the registers. And if it's not a load store architecture, it can even do these operations on memory directly. And of course, the CPU loads and stores data from and to memory. There's nothing more to it. Well, but actually, of course, you know, this is pretty simple. I didn't tell you the whole truth. If you look at this, I mean, in reality, it's quite a bit more complicated, and that's the PDP-11 from 1971. You don't need to know all about that, but that's a more realistic CPU model. And actually, that's a CPU model from a PDA of LSI. And you can see there's a lot going on. The memory is much more segmented, and you've got pipelines, and you've got execution units. And I didn't tell you about the cache, and I didn't tell you about lots of things, but you really don't know about that. So DMA, I just let everything out. Forget about that. There's one thing about the CPU that's very important, and that's the registers. Now, the registers are little memory units within the CPU that can be operated on and that have a special function. And in this very special case, the i386, which of course is all the Pentium and the Athlon and all the other more modern processors from Intel are quite backwards compatible. So we will just fix on that one, because that will be sufficient to understand what's going on. So we've got 8 general purpose registers, which are 32-bit wide. And 4 of these are just arithmetic registers. They are called EAX, EBX, and ECX, and EDX. And they basically are used for arithmetic operations. You will see what's going on there later. And actually, there's one thing about these registers. I mean, they look quite complicated. Why didn't they just call them A, B, C, and D or something like that? That's because they were extended. All this started, well, when Intel just brought out the first processors, like the 8080. And you can still address those 32-bit wide registers in bits and pieces. So you can just address the lower 8 bits, the lower byte, by just addressing AL. And you can address the the lower word with AX. And maybe you are going to, you're probably not going to need this, because most operating systems are working in 32-bit only. Okay, what we else have for address registers, they're used, well, as the name suggests, they're used for for addresses, and the most important ones will be the stack pointer and the base pointer. And we're going to see how they are being used. And there's one very important register, which actually is a kind of read-only address register. That's the instruction pointer. That's just a pointer where the execution flow is at right now. That means it points to the instruction that it's going to be executed at next. Well, okay, there are even more registers, but the 6 segmented registers, they're unused today because we have a flat memory model, and this is just, well, historic, for historic reasons. And the flags register, that's a register where some bits are set when maybe, for example, the last operation had yielded 0, and so that can be checked by the following operation. That's flags, and it just represents the status of the CPU. So let's go through some examples of the i386. And one of the most important ones, you won't believe it, is the knob. It's no operation, it's just do nothing. And we've got the move operations, like the second one here. It's going to store the value 17. It's hexadecimal. I mean, I guess I just suppose you know how you calculate that. It's the decimal value of 17, and it's going to be stored in the register EAX. Well, the next one would be, this is an addition, and the B that you can see right here, it just indicates that we have got a byte value. It could be a W if you are using a word, I mean 16 bits, or it could be a L if we are using long words, that would be 32 bits. But in this case, it's not clear if we're putting a byte, a word, or a long word. So we just designate with a B. So it's clear that we have an 8-bit value that is stored into memory. And there's one, this is a peculiar one. This one is called indirect addressing. And in this case, if the register is in brackets, it's not stored in the register itself, but it's stored into the memory address that is pointed to by the register. So actually, if you see that notation, it's just a pointer. So there are more operations that are quite important. Let's look at the push operation. I mean, it's that what you know when you're working with stack. The push operation just puts value onto the stack. In this case, it's the value of the base pointer that is saved onto the stack. And actually, if you go through this, you will see that the push is constituted of 2 sub-steps. The first one is to decrease the stack pointer by 4 bytes, which is just the width of the value we are storing here. And the next step would be to store the value of the base pointer to the address where the stack pointer just points to. We will see how that's going on in another slide. I mean, I will go into some detail there because this is quite important to understand what's going on there. The reverse operation of push, of course, is pop, and it just does the reverse. It fetches the value from the stack and stores it into the register that is given here. So this is just the other way around as designated above. This is just take the value from the pointer in ESP and store it into the base pointer and add 4 to the stack pointer. Some more examples would be the jump. It's just continue at the address given under any circumstances. It's just an unconditional jump to another address. And actually this, if this was possible, actually it isn't, this would be like just storing the value of the address we're going to jump into the instruction pointer. That's the whole idea behind the instruction pointer, because this one points to the next instruction we're going to execute. Okay, and the next instruction would be a compare instruction. And in this case, we're just seeing is the value of the lower byte in the A register equals 4, and if it's equal, we're going to set the 0 flag. And the next instruction just tests if the 0 flag is set, and if it's not set, it's going to jump to this address. It's a conditional branch we are looking here. So, of course, assembler instructions can also call subroutines, and that's this call here. This call pushes the return address, which would be the address of the instruction following to the call, onto the stack, and jumps to that address which is given here. And on the other hand, we've got return that would just be at the end of a subroutine that would pop the value from the stack and store it back in IP, in the instruction pointer. Well, one note on the byte order. Well, if you think about the decimal system we have got, that's big endian. And big endian just means it starts with the most significant byte, that's MSB. And if you just look at this example here, this is Motorola 68000 assembler. And what it does is it takes a big value, it's AA, BB, CC, DD, and stores it in the register D0. It loads the address 100 into the address register 0, and it stores the value in the first the D0 register to the pointer in A0. So if we look at the memory at this point, you can see that this is the memory address that's given here, 100, 101, and so on. And there starts our value, our first byte, the second byte, and so on. And it's stored in a way that we would write it down on our paper, like our decimal system. But there are just a few processes that do it that way, and it's most notably the Spark and the old Motorola processors, they do it. But on the other hand, modern Intel processors, they do it backwards. What they actually do is they store, this actually here is the same example as above in the Intel assembler, in Intel instructions. And you can see that it stores just the other way around. The least significant byte is in the lowest address. So, well, one can argue which is better or not. I mean, it's just a question how we look at it. So we're going to use that notation, and you will find all the addresses that are going to be pushed on the stack. They are just backwards, not like here. You cannot read them right away, so you have to well, think the other way around. Well, some notes on that, because some processes like MIPS and ARM and the new Intel processors, they're just configurable. They can do either big endian or little endian, and you can choose while you're bootstrapping. Okay, let's go into the memory model. This is a very simple segmented memory model, and actually this is very close to the model that Linux is using. And we have got the lower addresses on the top right here, and the higher addresses are right down here. And the first part of the memory is used for the so-called text segment, and the text segment contains all the instructions and all the static data. And this segment is just read-only. You cannot go there and modify the code, because that will give you segment violations. And after the text memory, the text segment, there's a data memory segment, and the data segment just holds all the global and static variables that you are defining in your C functions. And of course, it holds the heap that you can allocate by using the malloc functions. I mean, those who programmed C will probably have seen that. And at the very, very end of the memory, you will find the stack segment. And this actually is a stack where all the local variables are stored, and there's also control data, but we will see what that in the next slides. And the little arrow above here will just indicate that the stack grows towards the lower addresses. You will have to keep that in mind. So it will grow, not grow towards the end of the memory, but it will grow towards the beginning of the memory. Well, actually, there's one thing to add to this slide. You have to think about this layout. I mean, I've put some addresses right here. It's on Linux. It usually starts at 08000 and so on. And the text segment is very small, as you can see, and you've got very high values here. And this layout is actually the same for every process that you run on your system, because there's some memory management going on, and it's very important to keep in mind that you will see this situation for any process. So it looks from the view of the processes that they are all using the same memory, and that will be helping us very much when we are going to guess addresses, when we are going to need them, because they're always the same. You can expect the stack always to enter this address, and so you can make quite solid assumptions just by guessing. Okay, just as I said, the whole problem arises from the programming language C and all the derivatives, and we will go into how functions are called, and this is called the calling convention, and we will be seeing something about what a stack frame is, because that's a key point to buffer overflow. Well, I think we should see how this, what I've written down here, just actually comes. We just have a very simple C program. Okay, I hope you can see it. Can you, people in the last row, can you read what's going on there, or is it too small? Well, okay, I think that will have to suffice. Okay, what we have here, it's just a very simple program. You don't have to understand a lot. I mean, you've got a function, and it takes 3 parameters, just integer values, a, b, and c, and it returns an integer value. And what this function does, it has a local variable called d, and it just allocates a buffer of 100 bytes. And it just does a very simple operation. It just sums these parameters up and returns the value of the sum. Our main program, where the program started, it just is nothing much but declaring a value, and, well, you know what the result will be. It will store the value of 6, because it's a sum of the 3 parameters into the variable x, and it will return that variable to the shell that it's calling. It's just very simple and basic C that's going on here. And we will just now look through the debugger how this is looking in assembler. So we will just do some compiling on that. So there we are. By the way, this is not pure GDB, the debugger that comes with the new tools, but this is the Mammon extension. Well, it's called GDB Made Useful, in case you want to Googling for it. It's quite cool because it shows you the whole context that's running. You can see the value of each register that it now has, and you have a dump of the stack, and you can see the next instruction that is going to be executed. And what we see here is just how this line here looks in machine language. that actually is this part. So we can see 3 values are stored onto the stack, and we're starting with the third argument. It's just the value 3. 3 is pushed onto the stack, and then 2, then 1, and then there's a call to that function. This is how all this is working right there. So we may just go through it, and if you look at this stack part here, you will see the address where the stack is pointing to. You will just find it right here, there in that register, there it is. So we will be expecting the 3 value to appear right here if we are executing the next instruction. So there it is. It just got pushed onto the stack, and just mind it's in reverse order. And the same thing will happen with the 2 and the 1. And this is our stack. We've got the 3 values on the stack, and now there will be the function call. So we will see that the execution flow is going to take place. Well, yeah, there it is. And this is how the function itself looks like. I mean, this is not, no, it's too little what we can see. So this is the whole function. You can see each function is starting with a so-called prologue, and this is the first thing that any function does. It salvages or pushes the base pointer onto the stack because it must be restored afterwards, and it makes the stack pointer the new base pointer. We are going to see how that actually works out. Might be a little confusing right now, but just let's note what's going on here. And this line is very important in the end, because you can see the hexadecimal value 78, it's 100. It's just the size of the buffer we allocated. So we can see there's place reserved on the stack pointer for our buffer. And that's very important, because we now learned that the buffer is going to be in the stack. So what's going on here? You can see 3 values are added to the register, and we're going to return here. And okay, this looks a little confusing right now, but we will sum up what we found here. So the function is called by pushing the 3 arguments onto the stack and the actual call of the function. And then comes the so-called prologue. That's the beginning of any function. It's just pushing the base pointer and making the stack pointer the new base pointer, and then reserving space on the stack. And for local variables, I just forgot to note it there. Well, but the epilogue, that will be the leave and the return, whereas the leave is nothing else than just the reverse of what's happening here. We just had it. It was to restore the stack pointer from the old base pointer and to pop the base pointer from the stack. It's just the reverse of what's going in the prologue. So let's just get a little graphic. I mean, that was quite a lot of numbers there. We will see what's going on. What is going on here, you can see here, that's the calling, and the last part, that's the function prologue, the function that is called. And what is happening here, we're building a so-called stack frame. And that means any function is just, well, it's just building such a stack frame. We will now see how this is working. And the situation right now is these are the pointers, and this is our stack. And the stack is growing to the left. Well, and what you can see at the right, I mean, you can't really see, it's dotted. That is just an illusion. That means there's already been a stack frame that's on the right of this. So our stack pointer points to the end of the upper stack frame, and our base pointer points somewhere in that upper stack frame. Just, it isn't important where it's actually pointing. So the first instruction that's executed, that's the 3. The push, the 3 on a stack, and that's what happened here. And then the next one will push the 2 on the stack, and then the 1 will be pushed on the stack. So this is a function call. A function call, if you just try to recall what it was, it just puts the return address of the next instruction after the call onto the stack and, well, continues in the function. And that's where we here are. So then first instruction of the prolog, it was to push the base pointer onto the stack and to make our base pointer, which before the call points within the old stack frame, will just point right here. That's the situation right now. And the last step will be to reserve space for the local variables. So actually this is very much what our stack frame looks like. And you can see whatever is going to happen to the stack pointer, you might have some more space reserved or whatever you are calling functions or whatever. The base pointer, it remains static during the whole function. It just points to this location just above the local variables. So if you are going to access the function arguments, you are going to find them at a positive offset just from the base pointer. So it's each of these values here, the old base pointer and the return address are 4 byte. So you can find the first argument at an offset of 8, and then the next argument will be at an offset of 12, and at an offset of 16 you will find the third argument. And we can just have a look at that. It's just actually what's here going on. The second argument is taken first and stored into that register, and then the 2 other arguments are just added to that. It's just exactly what's going on there. So if we just sum it up, we have got space for the local variables just on the stack frame. And we just had a buffer of 100 bytes within the stack frame. And just let's think there's an operation going on that's filling that buffer, and it's copying a string into that buffer, and this operation is not going to stop until the string stops. So even if that buffer was 100 bytes, if our string is about 200 bytes or even longer, nothing will stop the buffer from overflowing. And it will just grow and grow and grow. And eventually, it will just overwrite all the control data that's in the stack frame, which of course is very bad. And eventually, it might even fill the stack frame of the calling function. Well, let's go into the exploitation itself. So what can we do with the overflowing buffer? Let's sum it up. We've got a frame a stack frame that with a buffer inside, and we control the buffer. I mean, there's some program trying to parse our user input, and it stores the input in a buffer and it doesn't check. So that's bad. So we will send that program a packet that we prepared, and that will be a lot of those no operations of those knobs. There will be some instructions, and there will be a lot of addresses. And this address, as it's drawn right here, shall be the address somewhere within all these knobs. Well, let's just see what happens if we put that into our buffer and overflow all the rest. So we've got a function going on. It's like the string copy function of C that will store the string into the buffer. It's just like I said before. This function won't stop until the string is 0 terminated. Well, that means the buffer might overflow. So this operation is going on and is overflowing the whole buffer, as it's drawn right here. And actually, you can see the base pointer that was on the stack and the return address that was on the stack, they are overwritten with a new address. So if the program now continues, the rest of the function will be executed. And well, just let's hope that it's not going to access some of the local variables or whatever, because all this is quite broken right now, because there's all the stuff that should be in the buffer. If the function now finishes the epilogue, you can see the leaf. It consists of two parts. The first part will be to restore the stack pointer from the base pointer. So this will be the result here. And the second part was to pop the base pointer from the stack. And you can see what happens now. Not the old base pointer will be popped from the stack, but the address that's written over there. So that address was just, well, some address somewhere within the knobs here. So our new base pointer points within those knobs. That's great. But the next instruction will do what all this is about. It will just return from the function, and that means it will pop the instruction pointer from the stack, and there also is our new address. So now our instruction pointer just points within all these knobs. Well, just let's say our instruction pointer just means the next operation that the processor will execute. It's just one of these knobs here. And we've got quite some knobs that we can try to hit with our address. Well, eventually the instruction pointer will grow as the knobs are executed, and the code will execute. And after the code, of course, there will be a lot of garbage. So one thing to note, our code should do, well, very proper exit, to clean exit, because otherwise the whole program would badly crash, because everything's pretty much broken right here. Well, this code we just saw, it will have to serve some purpose, and this code is actually shell code, because all this started by just executing a shell. Well, it's something evil that we do. If you're overflowing remote processes or remote servers, you can do even, well, nastier things like a connect back and attach a shell to that socket. Or you can alter the system configuration, or whatever you can think about. Just do whatever you want. And you should, in any case, you should exit cleanly. So let's see how we can do that in assembler. So actually here it is. That's our shell code. It's just a system call to bin shell and exit with a clean value. And if we just compile that, and execute it, we just see there's our shell. But it's running just with the privileges that we just had ourselves, so that's no point to it. Now let's see how this looks like. And there it is. You can see there are function calls, but they are pretty ugly. You cannot see what actually is called right here. So let's do a static link. Then we can see what's going on in here. That is. So you see, here's that system call. So let's see what's going on there. Well, there's even more, do system. So that's pretty ugly. So let's try another way. Well, sorry, I mean, the time is pretty advanced, so I'll have to make it a bit quicker. So if you do some research into the man pages, I'm very sorry about that, you will see that actually this is the call that will be made. So you have a call to this execve function, and you need a string, bin shell, and 2 null pointers. And this is the exit function. And pardon? Can you give him a microphone?
Type the wrong command line.
Oh, really? You should elaborate on that later. I mean, thanks. Okay. Let's see what's going on here. Here's the system call. Let's just go through the system call. That's the do system. That's it. You can see here it starts. You can go through the whole code, blah, blah, blah. And there's our execve call. I'm sorry, I will have to make this quicker. Otherwise, we're not going to do very much right here. If you go through all this, which we don't have time right now, you will find that this is our recipe for our shellcode. You will have the value B in the EAX register. It's just what you find from the disassembler output we just had there. And we will need a pointer to the string, bin shell in EBX. And you will have to have a pointer to an array that has itself a pointer to the shell string and to a null in ECX. And you will have a pointer to that null in EDX. And you will have a syscall to the Linux syscall table that's made by interrupt 80. And to exit cleanly is nothing more than to write the value 1 into the EAX register and to have the interrupt 80 called. And if we put that into a shellcode, this looks like that. It's just what we said. We have the value B in the EAX register and so on. And there's a string in here and the argument vector, how I called it, that's just the array I refer to, and the pointer right here. Actually, we can do some optimization on that. Okay, we can yeah, it's already optimized. Okay, well, there's one thing to note about that. The first thing to do in that shellcode is to jump to the end. And on the end, you will call the begin right here. And the first instruction that you're executing here, it's popping something from the stack. What was on the stack is a return address after that call here. And that address will be the pointer to that string right here. And this is quite cool because actually we don't really know where this begin here will be, and we will not really know where the string here will be located on the stack. But by this trick, jumping at the end and calling the begin, we will have just the value of the address here just on the stack, so we just pop it from there. And the rest of it is just a shellcode as we stated it. But if you look at that shellcode, you will see there are zeros within that shellcode. That's not too cool because actually we're dealing with strings, and strings, they're just zero terminated. That means, well, we shouldn't have zeros within that shellcode. So we will have to do some optimization, which I'm afraid I can't too much explain. I mean, this is the optimized shellcode, and you can see those values with zeros, they were replaced with some code that doesn't contain zeros. And if you just assemble it, no, we don't need it static. We just need it shell. Whoa. What's going on here? Oh, well, I think I have to explain it because... No, I can't explain it. There's no time to explain it. We just need the shellcode anyway. We can't execute the shellcode right from the shell. Let's just look at the object dump. So there it is. This is our code. You can see the jump, and to the end, you have the call to the begin. And this is actually the shellcode that we need. These are the bytes that our shellcode will consist of. And what I'm doing now is just put all this together into a shellcode test. This is our shellcode just in hexadecimal notation, and I just wrote what's going on in there. It's actually the representation of the bytes as seen by the processor. So that's the value that's in the data, and that's what the processor makes of it. And this just calls the shellcode. So this will just do it. I have to compile it. That's our shellcode. That's what it does. So let's put all this together. We've got a vulnerable program going on. Where is it? Vulnerable.c. That's a pretty stupid program. Let's just look at it. Well, what it does, it opens a file, TMP input, and it reads that input in a very large buffer of 1024 bytes, and it just does something with that buffer and writes something to a file. That's really very simple. And this do something, well, there's a smaller buffer, and the whole string that was contained in the input file will be just written into the buffer. And, well, what you can see is if the buffer here is very much longer and the string inside it, it would just make a buffer overflow right here. And there's nothing going on here except stripping the following returns from that string and just printing some debug information. So that's our vulnerable program. Well, and to just take advantage of all that, we will have to make this a root program. So what we have here is an unprivileged user. Okay. And we will just put some data into that input file and just execute a vulnerable program. So what it did, it wrote all that into its log. It was called daemon log. So there it is. The message was hello. Well, it will do that very much as often as we want. And it will log that information that we gave to it into that file. So, but as this program is just running as a root, and no, actually it's not yet. So now it is. It has the setuid root bit, and it will execute with root functions privileges. So let's just put an exploit together. So here's our shellcode. And what's going on here in the routine is this thing will take 3 arguments as a value called nopfill, the return address, and the return fill. And this one just puts the nopth into the output. It's just the character 90. That's the instruction nop. And at the next, the shellcode will be written to the output. It's like that one here. And in the end, we're going to append some return addresses that will just go over the control data. And oh, great, I've already got it here. We just knew our buffer would be about 512 bytes, so let's put 400 nops in there. And in the end, we will have an idea about where the buffer lies. That was like BFF. Yeah. It should be somewhere around here. I mean, we could go through the GDB and just look where actually the buffer lives. But we have got 400 nops to meet, so we can just have a good guess right here. And let's append some 30 return addresses in the end. So that went to standard output. It doesn't look very cool. Let's put it into that file that our vulnerable program is going to execute to process. It was TMP input. Okay, we're still unprivileged user, and just let's give it a shot right here. This is our packet that we made. It's a lot of nops, then there's a shellcode and a lot of return addresses, and that's going to overwrite the stack frame just right here. So our vulnerable program is going to process the input file, and the buffer will be overwritten. That's not so good. Let's try some other addresses right here. Damn. Let's try some more. Let's try for 40. Let's see what's going on there. So we had just some debug info output. So this was the address of the buffer. I just had it printed here. And let's just try some address in that space. So you see, this pointed just before our buffer, so that really can't work. Let's just try something above that for 70 or something like that. Whoa, there's our shellcode. And now we've got root privileges. Thanks. And we just instructed the program to do things it just wasn't really meant to do. And that's pretty bad. Damn. So what can we do against all this? I mean, just learn how to program. That's the best thing to do. I mean, don't use string copy. That's the first thing you can tell everybody. I mean, just use their counterparts that will be limited to a number. They're called string ncopy and string ncat and string ndup, and they're just great. You can just give a maximum size for the buffer and everything is great. Do proper user input sanitation. I mean, don't trust user input. Just be very specific with it. I mean, just look very close at it. I mean, there are people who are trying to overflow your buffers. And you can do proper testing of your code. I mean, fuzzing is, well, you can learn more about this on, well, I mean, tomorrow or the day after tomorrow, there's a course about fuzzing, what's going on there. And you can use some stack randomization patches like PAX or exec shield. And actually, I just learned the Linux kernel from 2.6.12 on has built-in randomization. And I will just show you how that works. And in the end, you can, well, you can look at the non-executable bit. You can just make the whole stack where the shellcode is not executable. But there are ways around it because it's very badly implemented in the processors. So just one thing to the end. You will see that buffer overflow here works. It's just great. And if we just turn on the stack randomization in the Linux kernel, it's through the proc interface in that variable here. Now it's turned on. And you will see the overflow doesn't work anymore. I mean, the program crashes very badly, but the return address is not right. It's just because the stack pointer is now variable. It changes its value from call to call. So the memory layout is not the same for every process that we execute. And, well, that doesn't look very good. And so the chance to find the right address when we are trying to overflow the buffer, they're very limited. So just use a proper kernel and you will be quite safe from that. Well, okay, that's it. I mean, you know, there was a problem to have all this very short, and the time was pretty tense. So I hope you could, well, learn a little from that. And thanks for being here.